Today, I want to talk about a series of techniques that are very important for machine learning, specifically ensemble approaches. So let's dig into that. Ensemble methods are one of the most powerful and practical techniques in machine learning. And the core idea is simple. Instead of relying on a single model, we combine multiple models to get better predictions. So we'll cover today several topics. First, we'll understand why ensemble work, the mathematical intuition. Then we'll look at majority voting, combining different classifiers. Next, bagging, using bootstrap samples to create diversity. And then add a boost, boosting weak learners into strong ones. Finally, we're going to take a look at gradient boosting and XGBoost, which is the state of the art. So what's the goal here? We want to combine multiple classifiers to build a more robust model. The key insight is this. Individual classifier make error, but if those errors are uncorrelated, meaning different models make different mistakes, then the ensemble can outperform any single model. Think of it asking 10 experts for their opinion. Even if each expert is imperfect, if they make different mistakes, averaging their answers give you something better than individual. Let's make this mathematical. Suppose we have n classifier, each with error rate epsilon, that's the probability of being wrong. For a majority vote to fail, more than half the classifier must be wrong simultaneously. This formula uses the binomial distribution to calculate that probability. So epsilon to the power of k is the probability they're all wrong, and we sum over all every k greater than half of n. The cases where the majority fails. You need to be familiar with the choices of k out of n. It goes back to some of the basics of permutation and counting, but essentially there are how many ways that you can choose k different of this classifier out of the set of n, and then you want all this k to be wrong, so the probability of them to be all wrong should be each of them epsilon, so they're going to be multiplied by each other, and the rest they're correct, which are 1 minus epsilon to the power of n minus k. Think about it. Some of these mathematics you can write it down, spend some times, or discuss with TAs. So let's do some numerical examples so that we understand this better. So with 11 classifiers, each having 25% error rate individually, the ensemble error drops just to 3.4%. But notice what happens at 50%. If your baseline classifier is no better than random guessing, the ensemble doesn't help at all. So the key takeaway is this. Ensemble only help when each baseline classifier is better than random. Now let's talk about how to actually combine classifiers. There are two main strategies. Hard voting. Each classifier casts a vote and we go with the majority. That's like a simple democracy. Then soft voting. Each classifier gives probability estimates and we average those probabilities. This is often better because it uses more information. So as you see, for example, classifier 1 votes A, classifier 2 votes A, classifier 3 vote B. So that means 2 classifiers vote A, 1 votes B, majority wins. The formula at the top is the formal definition. So here's the concrete example. We have 3 classifiers. Classifier 1 says 90% class 0, classifier 2 says 80% class 0, but classifier 3, which has the highest weight, says 60% class 1. When we compute the weighted average, we get 58% for class 0 and 42% for class 1. So the ensemble predicts class 0, even though the highest weighted classifier disagreed. This is the nuance of soft voting.